Hi guys and girls, in this video we're going to talk about components and specifications, going from basic level to intermediate level. Now we'll start with the diode. This explanation is specifically designed for those building the bedini schoolgirl and then wanting to progress from there into other methods. Now we'll start with the diode. It is the 1N4007. Now most people think of the diode as a valve, and it lets current flow from one side to the other. In the most part this is correct. However, there are issues with diodes. First of all, you will need to go and grab the datasheet for the 1N400 range. The same datasheet has all 7 types of diode for the 1N400 range. So grab that datasheet. I personally grab most of my data sheets from alldate.com. So if you want to go there and download them, that's fine. If you have your own source, go right ahead. But pull the datasheet up on your screen, and it should look a little bit like this. The 1N400 range are from On Semiconductor. These data sheets, just for YouTube, who seem to like to pull my previous explanation of components down for copyright infringement, which is complete lunacy considering these data sheets are given out free. But oh well. And you can see here at the top, I'll just curl this up, all 7 diodes are listed here. Axial lead standard recovery rectifiers, that's what they're called these days. Most helpful. Be careful with data sheets. You can come a cropper with them. I have done so recently. They like to put things in awkward places where you miss them and write things in a manner which you would just not think anything differently of. Anyway, the main thing that we're looking at is these tables here. I have a sneaky suspicion you cannot read that lot, but if you've got the datasheet in front of you, it'll be okay. Now, across the top of this table, hang on, I'm going to move the camera instead. Job done. Across the top of this table here, really? Bugger off. Really? No? Oh, pressing down on that. No, go away. Okay, is the part number. So here on this side you have the 1N4001, and on this side you have the 1N4007. What is the difference between them? Well, that's what this table tells you. First of all, peak repetitive reverse voltage. That is basically the maximum voltage that can be applied in the opposite direction of the diode, so basically going against the valve. So the 4001 is 50 volts, the 4007 is 1000 volts, hence why the 1N4007 is used. Non-repetitive peak reverse voltage, right? Now you've got a continuous voltage and you've got a peak voltage. In this case 60 versus 1200. Right. RMS reverse voltage. Well, RMS is an average method. It means root mean squared. Look it up. There's plenty of wikis about it. In this case, 35 versus 700. Now, that's all well and good. That gives you a threshold for basis for your diode. So if you're doing high voltage experiments, you need the high voltage version of the diode. Now, going down again here, we've got average rectified forward current. Yay. Right. What this means is the current flowing through the diode as an average. Right. Again, these are maximum ratings. All of the diodes are rated at 1 amp. If you've got the data sheet in front of you, you'll be able to see this. So there's no difference between the smaller one or the smaller one, the lower voltage or the higher voltage one in terms of average. This can be good, this can be bad. Make sure that your application doesn't even it's an average, but anything over the value rated there, in this case 1 amp, you start to lose excessive amounts of power because the diode becomes efficient at switching it. Inefficient at switching it, rather. Non-repetitive peak surge current. Well, here we go. Non-repetitive peak. Basically, if you put a spike through it, right, it can be non-repetitive, as in once in a blue moon, once every day, couple of months. It really doesn't tell you what non-repetitive actually refers to. But in this case it says the maximum it'll handle is 30 amps. But again, don't forget, above 1 amp, which is the rating that's above it, above 1 amp, the diode becomes inefficient, and increasingly the more current you try to shove through it. My advice is, if there's a possibility that you're shoving a significant number of amps through it that is its initial average rating, my advice would be to do either double up on the diode or select an alternate. Some people double up on the diodes because they actually have them there, and it's easier to just solder a second or third diode in. I've done it myself many times. And finally, the spec at the bottom. Operating and storage temperatures. Well, it gives you the range, but you've got -65 to 175 degrees centigrade. Anyone running them outside of that, I will be impressed, to say the least. Now, some of the more interesting specifications are actually on page 2. See here. Comes under the section of electrical characteristics. Maximum instantaneous forward voltage drop. Yeah. I had fun with this one when I first started out with datasheets. Basically, the forward voltage drop is the loss of volt that is caused by the diode. So in this case, the maximum forward voltage loss is if you were putting the maximum amount of current through it. That's the voltage that you would lose from one end to the other of the diode, which in this particular case, the typical is 0.93, maximum is 1.1 volts. So straight away you can see there is a huge voltage loss on these diodes. Maximum full cycle average forward voltage drop. What a frigging mouthful. I'm sure it means something, but I've never been able to tie up what the hell that actually means. It seems to be some sort of weird calculated average, which, well, the only thing I can say for it is it's below the maximum. So there we go. To be honest, I find it irrelevant. I've never really looked at that figure, so I just completely ignore it. Maximum reverse current. There you go. It states it in the datasheet. Reverse current. Right. That means there's a backflow from, if you were using this on a simple schoolgirl. Oh, tablet's kicking in. If you're using this on a schoolgirl to charge a 12 volt battery via the back EMF, you will get a backflow through the diode from the charge battery through the coil. It says so here. This value I find to be completely and utterly false, but there we go. It says typical value of 0.05 microamps with a maximum of 10 microamps. As I said, I find that to be completely rubbish in most circumstances. Now, what isn't mentioned on here, which is why I find that last figure oh wait, there's one more. One that's on here, this bottom line. Maximum full cycle average reverse current. Again, what a mouthful. God. It's to do with the full cycles of forwards, backwards, forwards, backwards, forwards, backwards, etc., etc. The interesting thing is here, the typical is just has a dash on it. Probably means they can't be asked to test it, or do an average, or do something about it. But they say the maximum is 30 microamps. It gets a lot worse. What isn't in the datasheet is significantly important. I just realised I didn't print an example. So just bear with me 1 second. There we go, page 2 of this. What isn't mentioned anywhere in this datasheet is time, specifically recovery times. Now, on this particular diode, it's a Schottky diode. Okay, you've got the forward voltages here at various currents, right? It's the forward voltage that requires it to operate. Right? This one's one of the more expensive diodes, and they do a lot more testing, so you get what you pay for. So with a forward current of 1 milliamp, the voltage loss is 240 millivolts. At 1 milliamp, you lose 320 millivolts. At 10 milliamps, 400 millivolts. 30 milliamps, 500 millivolts. And at 100 milliamps, you lose 800 millivolts. That is also drawn out on a graph further in the datasheet, and you can take a look at that and work out what your voltage loss is going to be from the graph. However, what we are looking at here is the reverse rectify time. It tells you on here the time it takes for the diode from being fully open to fully closed, and in this particular case it says 4 nanoseconds. As I explained, this is a high quality diode. It isn't suitable for all applications, right? So don't just ask me what this diode is. You need to tailor it for your own, which is why I'm telling you, explaining what the datasheet is and what the figures are for. Now, you also have a diode capacitance on here, which if you're doing any sort of resonance work, you need to take that into account. But other than that, look out for the data sheets that show you recovery times, on time, hold times, stuff like that, as I will show you shortly. So that's diodes that we've gone through. Now, the fun bit is transistors. Most people explain a transistor is a switch to a point, correct, in layman's terms. Okay, we have the 2N3055, and there is also its sister, if you like. The 2N3055 is an NPN transistor. The MJ2955 is the PNP version. On a simple schoolgirl, you cannot use the PNP version as the circuit stands. Now, if we go to the symbol for the transistor, for the NPN version, you have to apply a voltage to the base that is higher than the voltage at the emitter. So current can flow from the base to the emitter, which then turns the transistor on and allows an even bigger current to flow from the collector to the emitter. Kind of simple. If the voltage to the base is shut off, so it is below the voltage on the emitter, equal to or below, then current does not flow from the base to the emitter, and therefore it shuts off and stops the current from flowing from the collector to the emitter. Now, the information on the datasheet here, we have some interesting. Right. Collector to base voltage. Well, in neither of the scenarios that I've just told you have I mentioned anything about collector to base, which is true in a normal operation for a transistor. The voltage between collector and base is irrelevant. However, because this is a silicon device, it has maximums, and that's what this is. So the maximum voltage from the collector, so up here to the base, is 100 volts. If you exceed that, you get a breakdown in the transistor, which allows current to flow from the collector to the base. This can be bad. Any breakdown in the transistor shortens its life significantly. Collector to emitter voltage. Right. Again, collector to emitter. If you increase the voltage beyond this rating, it will cause the transistor to break down and current will flow from collector to emitter. In this particular case, it is 70 volts. Now, you've also got a second collector to emitter voltage. Basically, it's under a slightly different condition, as stated on here, and it's saying 60 volts. Yes, I'm reading these upside down. Now, these conditions kind of difficult to follow. My advice is go with the lowest, unless you know how to replicate these conditions and what these conditions actually mean. Right, emitter to base voltage. This is the reverse voltage. Remember I said that the voltage on the base, when it's higher than the emitter, allows current to flow from the base to the emitter, turning the transistor on. Right, if the base voltage is below the emitter voltage, right, the maximum voltage is 7 volts. This is why the Bedini simple schoolgirl has a diode that goes from the emitter to the base of the transistor to prevent the emitter voltage going over the base voltage by 7 volts, which would cause a breakdown in the transistor. Collector current. This is the maximum amount of current that the transistor itself can switch. Exceeding this, you're likely to blow the crap out of the transistor. So, my advice, don't do it. If you need to, you can double up on transistors. Base current. This is the amount of current that can flow from the base to the emitter. Right. In this particular instance, it's 7 volts. Sorry, 7 amps. Do not go above it, you will damage the transistor. Total dissipation at, well, it says temperature is 25 degrees. This is the amount of power that is being lost as heat from the transistor. Right? And this is absolute maximum, which in this datasheet is 115 watts. Storage temperature, again you've got minus 65 to 200 degrees centigrade. Maximum operating junction temperature is 200 degrees centigrade. In other words, be careful when you're soldering it. Now, they're the absolute maximums. Right, electrical characteristics, this is where life gets fun. Right, collector cutoff current. Now, it has two conditions here. Which we're going to ignore. One is temperature rating, but it says the cutoff current for the collector is 1 milliamp at room temperature. So if the current flow from the collector to the emitter is less than 1 milliamp, then the transistor will automatically shut off. Which means for certain low power applications that transistor is not suitable. Collector cutoff current, well, we've got this in here again. They just love to throw in the scenarios on these. In this particular case, it's a change in voltage basically, and it says 0.7 milliamps. Okay, pretty much the same as the first one. Emitter cutoff current. Well, never could understand that one. The symbol is IEBO. To be honest, I've found it completely irrelevant most of the time. I'm sure someone's going to correct me on these. However, it says 5 milliamps. My advice, just assume everything's 5 milliamps from the above anyway. Now, collector to emitter sustaining voltage. That's an awful way of writing that. I love the way that that's written. I really do. Okay. I hate that one. Well, it says the collector to emitter sustaining voltage, minimum voltage is 60 volts. That is one of the things that is so misleading, it's unreal. My advice, ignore it. Collector to emitter sustaining voltage again, under a different load, it says 70 volts, my advice is to ignore it. As long as you do not go above the maximums, you will be fine. Now, this is where we get the interesting bit. There is yet another collector to emitter sustaining. It's not sustaining, what's that word? That's it. Collector to emitter saturation voltage. I told you this gets fun. The saturation voltage is what is important here. Now, there are different conditional tests. Basically, the voltage difference from collector to the emitter, right? The minimum to maintain an on voltage, right? In this case, at room temperature, up to 4 amps, with a base current of 400 milliamps, right, is 1 volt. If you are pulling 10 amps from the collector to the emitter, and your base current is 3.3 milliamps, then the saturation voltage is 3 volts. Right, basically, it's the minimum voltage difference. which means if you're operating less than 1 volt on this, probably higher than that, but then this transistor will not work for you. Base to emitter voltage. Again, this is a saturation voltage, even though it doesn't tell you. The base to emitter voltage may be listed as base to emitter saturation voltage, is the minimum on state voltage, as in your base voltage relative to the emitter has to reach this minimum voltage in order for it to turn on. Right. In this case, 1.8 volts. So you have to give it 1.8 volts for it to turn on. There are conditions here, specifically with a current draw of up to 4 amps. DC current gain is great fun. It's to do with the operation of the transistor. As a general rule, I don't use it that much. It's been a while since I've needed to know the gain. So for most people, my advice would be to ignore it. If you wanted to look it up, go right ahead. You might find it useful, you might not. Transition frequency. This is the fun bit. It's labelled up as transition frequency, which is frequency from one state to another, i.e. on to off, and how fast it can do it per second. Now, for the 3055, it only lists the minimum, which is 3 megahertz, which is nice and quick. Now, in that, you can discover other things which I'll come back to. Second breakdown collector current. Second breakdown collector current. Yay! This is a very fun figure, which I'm going to try and explain. And yes, I know this video is getting on in time, so I'll try and pick things up. Transistors have 2 breakdown modes. One is called a soft breakdown, the other one is called a hard breakdown. In a soft breakdown, essentially all hell breaks loose. Current can flow in and out of any pin that it wishes to. Basically, the transistor becomes a flat conductive path, is the only way that I can describe it, which is quite dangerous unless you know what you're doing. In a hard breakdown situation, one of several things can happen. Either the transistor literally welds itself in the closed position, basically melts down in its internals and connects all the pins together, allowing current to flow any which way it wants. Or it can break down in an open state so that everything is isolated. Now, the cheaper transistors that are not avalanche rated generally tend to break down in the closed position. Now, depending on your circuit, this can have the effect of vaporizing the transistor. In other words, it goes bang. Now, those that fail in an open position, basically you just get a whiff of burning component, and then that's it. It stops working. It's quite safe. I always recommend avalanche rated components because they are much safer. They don't go bang. Well, most of the time they don't go bang. Most of the time they also don't set fire. But what can I say? Most of the time. Those components aren't, be very careful with. The use of a CO2 fire extinguisher would be advisable. Definitely don't use water. If you wanted to attach temperature probes to them, that's definitely advisable, especially when you're first starting out with a new circuit. Once, of course, that you have ran the circuit for a couple of days and nothing untoward's happened, then obviously you don't need so much safety kit. Now, going back, transition frequency stated here is 3 MHz. This is the maximum, well, in this case the minimum frequency that it can go from on to off and then back to on. Right. From this you can work out what the on-off times are. Right. But it doesn't actually tell you. Now remember, the transition from off to on and on to off is not instantaneous, and basically it's a gradual slope. The shorter the on to off and off to on times, the better. Now some transistors actually tell you what these times are. Some of them don't. Certainly transistors that are in the millisecond range are not so good, but some transistors that go down to the nanosecond range you get interesting results with. So have a look for the transition frequencies. It may also be listed as rise to fall time or fall to rise time. You've also got the on delay or off delays, stuff like that. But as always, look at the datasheet. If there's something in the datasheet that you don't understand, then down the left hand side you have symbol. Type the symbol into Google and have a look at the wikis for it, because the wikis will tell you what those symbols actually mean. Okay, and some of them are also in English so you can understand them. So that's pretty much everything I can think of on a transistor, which is pretty much all the components that are used on the Simple Schoolgirl. So for those that are beginners, my advice: do not exceed the maximums under any circumstances. Always use inline fuses, whether it is a standard filament fuse or one of the newer thermal fuses, or even an RCD, which I've used myself. Sorry, not an RCD, a circuit breaker. I've got two 5-amp ones on my bench in the garage, which I showed many years ago. What else can I say? Be safe, as always. Take it slow, no need to rush things. If in doubt, as always, ask, and don't trust one source. If someone tells you one thing and another person tells you something else, so the two are conflicting, go and ask a third person. Right, let 5 or 6 people tell you, and then go and find out, is my advice. Plenty of reading is always in order, and don't forget basically to use your eyes, use your ears, and most importantly use your own brain. It's not that hard. You just need to read and learn. Hopefully this has been a help to people. Not sure when the next video will be or what it will be, but have fun as always. Take care and be safe. Bye for now.